So 4.6, we're going to talk about it. We're going to talk about it again tomorrow too, and do a bunch of examples. Related rates. Related rates is why Newton invented calculus. He wanted to see how things were changing in terms of other things changing. Like, for example, if you're on the train, you know what I'm saying? You see those bushes just flying by right in front of you, and you see that tree out there and it's going really slow. How fast is that tree really moving in terms of mean? Because it's going slower than that bush that just went by, even though neither of them are moving. You know what I'm saying? In terms of you, those bushes are flying by, but that tree, that's taking its time. So, like, what's the relationship? There's got to be some relationship. And that's what Newton was interested in, figuring out those types of relationships, setting up some model, and figuring out how things are changing in terms of other things. That's why he invented all this stuff. So 4.6 is related rates. And let's start here. Do you guys remember, I don't know if it was in Math 3 or Math 4, the oil spill problem? We spilled oil and then it was growing.
Yeah.
Was that last year? It's so sad. Yeah. Alright. So, you got some oil, and it's at some point, and then it's spilling, and the oil spill's getting bigger, and it looks like a circle. Yes? So it starts here, and then like a couple minutes later, it was like here. The oil spill's getting bigger. Yes? Okay. What's a general equation I can figure out for like how much oil is on this top part right here? Like on the surface. Yeah, area of a circle equals pi r squared, yes? Okay, so there's a general relationship between this oil spill is the radius of this circle and then the area. Now, as this thing grows, does the area change?
Yes.
Does the radius change?
Yes.
What that means is, and I'm sorry, and it changes in terms of time. So before, I think a couple of sections ago, we took the derivative of A in terms of R. And what that would be is, what we're asking is, okay, how's the area changing, or how much is it changing as the radius changes? When the radius is this big, how fast is the area changing? Well, what we can also do is say, how much is all this stuff changing in terms of time? And you can take the derivative in terms of time. And this thing changes as time goes on. And this thing changes in terms of time. So I can ddt both sides. Do you guys know what ddt is, that chemical? That's like, well, we're all poisoned. Does anyone know what I'm talking about?
Yeah.
Insecticide. Oh, I didn't know that, bro. Wow, it just got said. Okay. It's sort of like the farmers, and it's like in the soil, and we can't get it out. Anyway, all right. So I dA dt. What's that equal to?
dA dt.
Yeah, dA dt, or a prime, however you want to write it. Now I'm going to write it as dA, the change in area over change in time. This is changing. Now what's d dt of pi r squared, and how would you do that? It's 2 pi r
Circumference.
times,
Oh, yeah.
nice, notice that. And in this case, since like we're not doing ddr would be 2 pi r times dr, which is 1. This would be, bring down this is a constant, pi. I bring down the 2 times the derivative of what's inside. 2 pi r times dr dt. Now what this is it's an equation, formula, function, that'll calculate if you know how much the radius is changing. You could figure out at a certain r, at a certain moment in time, if I tell you, hey, when the radius is this big, how fast is the area changing? So this is a new equation. It can tell me different information. But I need other information than just a equals pi r squared. See what I'm saying, you guys? This is an equation that tells you how things are changing, the relationship between how the area changes and how the radius changes in terms of time. So if I told you, hey, this oil spill, if this was the oil spill problem, okay, it's growing at, the radius changes at a rate of 5 feet per second. Okay? And I want to know how fast is the area changing at a specific moment when the radius is 10 feet. Well, do I have enough information to figure that out now? Sure. If I want to know, okay, so I have my area changing equation that I created. Well, I know that the area changes in terms of time. Well, let's see, it's 2 times pi times the radius. And what moment? What moment you want, Mr. R? I want to know when the radius is 10 feet. Okay, and I know dr dt. It's a constant change of 5 feet per second. And you guys notice, as at different r's, you're going to have different changes in area. You see that? The bigger your radius, the faster the area is going to be changing. Do you see that, you guys? Because it's that sort of direct relation. You make this bigger, if this is constant now, these are all numbers. That gets bigger, that gets bigger. Okay? Now, what I like about these sorts of problems is, check this out, Jessica. Did you see what happens here if I multiply all this together on top? What do I get?
100 pi.
I get a 100 pi times, or 100 pi, and then what's my unit? Yeah, treat these like a variable. You know what I'm saying? And if you treat your units like a variable, it'll help you solve the problem. So I get 100 pi feet squared per second. And is this a make sense answer for my change in area over change in time that I have a number square feet per second? It matches up, and it should. Does that make sense, you guys? Your units should match up. If they don't, it's a good check for you, Wayman. Just like in chemistry, if you know your stoichiometry, the units will tell you how to solve the problem. In this case, if you take your derivative and then you match up all your units, and then you get like cubic feet per second, that's not a change in area over change in time. You did something wrong. You know what I'm saying? Or if you just get feet per second, I did something wrong. So then you can go back and check. You know what I'm saying, guys? So let's try another one. Did we like that or no? You did? Alright! Alright. And I'm going to get a haircut over break too. Is it? See how it feathers on the side? You see that?
Yeah.
Isn't that good stuff? Jealousy. Okay. Here we go. Don't worry, guys. It'll be nice and... Barbers aren't open on Sundays. What are you going to do? I got a cylinder. What is the volume of a cylinder? How do you figure out that equation?
Square, times height.
Yeah, you guys remember that? It's the area of the base times the height. Yes? Good way to remember. You're going to run into a lot of these types of things. And how do you figure out the equation? Well, it's the area of the base, which is a circle, times the height. So volume equals pi r squared h. Now, if I'm filling this stuff with filling this thing with water. Here's me. This is a serious drawing. There we go. It's like a cord. It's supposed to be hair. It's a little shaggy because I haven't got a haircut in a while. So if that looks good. So if I'm filling it with water, you know, it starts out here, then a little bit later, it's here. I'm going to ask you this question. Looking at this volume equation, what's changing and what's not? Talk about it in your group. As I fill